Welcome everybody. I'm quite happy to be here. Thanks again for the invitation. Much appreciated. It's my first time here, actually my first time to Russia. So up to now I'm enjoying it a lot. So let me quickly introduce myself. I'm Jan. I'm working for Linutronics, which is basically a service provider for embedded Linux. So we are porting Linux to new hardware and stuff. So we are located in the southern part of Germany, so at the Lake of Constance. You might have heard about that region. It's basically where most of the Germans spend their vacations. So I'm in the lucky position that I can work in that part of Germany where just most of the people can only go for their vacations. So that's actually pretty nice. But apart from being located in a nice area, we do a lot of things regarding to industrial Linux. And one thing we've been doing for like more than 10 years now is getting real-time capabilities into Linux, and that's basically what I would like to talk about today. Well, let me give you a quick overview of my presentation. Well, I don't want to be boring, but well, I will start with a quick introduction of what is real-time. You know, I know every talk about real-time is starting by answering the question, what is real-time? So I just need to keep up with that tradition, right? No, but to be honest, there's, especially when it comes to Linux and real-time, there's sometimes some misunderstanding what we are talking about. I just want to clarify what we are doing at Linutronics and what's the main goal. Well, then I will give you a historical overview of real-time Linux, which is basically somehow also my personal history, because I'm working on real-time Linux systems like since 2002. So we have several approaches to bring real-time to Linux. I will just show you some possibilities how you could get real-time into Linux, and well, you will see I have a strong recommendation what you should use when you want to use real-time on Linux, and that's basically the so-called real-time preemption patch, which is, as you will see, a patch set which is pretty close for being integrated in the mainline kernel. I will just tell you a bit about the techniques, how we are trying to get to real-time in Linux, and I will also tell you a bit about the status of the mainlining efforts we're doing. Well, and at the end of the day, I would like to show some benchmarks, which are basically some latency measurements on different approaches of real-time Linux. We're just measuring basically the reaction time, how fast you could possibly respond to an interrupt event. So what I'm comparing right here is just Xenomai and preempt RT. I'm going to tell about these technologies later on. And basically at the end of the day, as already mentioned, I'm going to give you some strong recommendation what you should use when we're talking about Linux and real-time. So let's start with the, as promised, definition of real-time. So there's still a lot of confusion when we talk about real-time Linux. So if you would go down to the road and ask people about real-time, what would they tell us? Well, basically it would just tell us the time of the day, right? And well, we have the same confusion in Linux. We have a clock real-time, but that's not what I'm talking about today. The clock real-time is just the time of the day, but that's not what I want to talk about today. And it's also not, this is another misunderstanding we usually have. We don't really talk about real fast execution times. Can be, but not necessarily. Another misunderstanding we usually have is, well, is real time about performance, fast execution times and performance? Well, no, it's basically not. So what I would like to talk about today is, it's basically deterministic timing behavior. So you want to respond to an event in a given time frame, and this is basically a requirement usually industrial customers have. They have to react to an external event within a very limited time frame, and they have to guarantee these reaction times. And this is basically what I would like to talk about today. So this means that the correctness of the execution is not only depending on your algorithm or your implementation, the correctness is also depending on the execution at the correct time or within the correct time frame. This is pretty important, so which means if you miss the correct time slot, this will lead to an error condition. So at the end of the day, this means missing the time slot, it's an error condition. So the practical point of view of this is if you miss the time slot, that's an error condition. So this means that might cause any damage to your machine or actually might hurt a real person, right? So actually my nephews had quite some fun to get me prepared for that picture. So basically we are talking about deterministic timing behavior today. That's basically all I want to say right now. But there's actually another word I would like to clarify right now. One word we really hear often when we talk about Linux in real time is the so-called soft real time. So people tell, well, Linux can do real time most of the time, so the average is pretty good, but sometimes we miss the timeline. Well, you know, if this is the result, obviously I don't want to miss the timeline, right? So it's the same for determinism. So your operating system can be deterministic or not. Nothing in between. That doesn't make any sense. So basically, please forget about soft real time. So in my opinion, that word doesn't actually make much sense. So I usually do the comparison if your girlfriend would tell you she's kind of pregnant. Would that make any sense? No, it does not, right? So it's the same for the operating system. It can be deterministic or not, but nothing in between. Okay, so well, if real-time Linux systems are quite new for you, you might be wondering if there are already people using that, and the answer is yes. There's many people already using Linux in real-time critical environments. There's like, you have the classical automation industry like machine controllers, numeric controls and all that stuff. So we have already many people using Linux on these machines. We have multimedia system. We've got aerospace, like they are using it for simulation, for testing environment and a lot of stuff. So they also have hard timing requirements. And actually, what you can see right here, we're even using it for financial services. So, well, that might sound a bit weird, but well, what these guys do is they have to calculate a lot of transactions in a given time frame in the correct order. So if they miscalculate or do it in the wrong order, so some people might lose quite a bunch of money. So they need to guarantee some timings, and actually these systems are running real-time Linux. No joke. Yeah. So this is actually real-time Linux running on real big server machines. So we already have many users using Linux in real-time critical environments. So how could we basically get real-time to Linux? Well, the main problem is that Linux has never been written as a real-time operating system. So we have a couple of requirements we need to bring to Linux, like, yeah, I told you, deterministic timing behavior. So the most important thing we need for determinism is we need to be preemptible, and we need to be preemptible as much as possible inside the operating system. And well, apart from that, we have to deal with a couple of special situations which are very specific to real-time systems. Like we have a special situation which is called priority inversion, very specific to real-time systems. So I've got an example on this right here. So this is actually pretty simple. We have 3 tasks. Task number 1 is the highest priority, task number 3 is the lowest priority. And these 2 tasks have to share a resource, so we need some kind of synchronization method, right? So that's actually not a big deal. So, but now what could happen is task 1 is running, which is the highest priority task. And well, it gets blocked because task 3 is holding a resource they are sharing. So that's also not a big deal. But now what could happen is we have a task with a priority in between, which is now interrupting task 3. So it can't free the resource and the highest priority task gets blocked. That's a very classic failure situation in real-time operating systems. We call this priority inversion because the high priority task is waiting for the low priority task. So these are situations also a real-time operating system needs to deal with. So what we basically do in Linux, and Linux already can deal with that without any extension. We use priority inheritance, which means in that situation, we'll just boost task 3 to the priority of task 1, just for the time they are sharing the resource, so it just can't get interrupted. So that's priority inheritance. It's already supported by Linux without any extensions. But you see, there's many requirements we need to be aware of when using real-time. So how can we move, or how can we fit these requirements with Linux. So we have basically two different approaches. We have the so-called dual-kernel approaches, and we have the single-kernel approaches. So the second one is basically making Linux itself real-time capable. Let me quickly look into these approaches. So this is the very classical approach, the so-called microkernel or dual-kernel. These are the very first approaches of making Linux real-time capable, just had this design. So what these guys did was, instead of reworking the whole Linux, they introduced a small microkernel, which is just responsible for the timing critical tasks. So basically everything which needs real-time capabilities is running inside here, and Linux is just running as a low priority task on top of it. So if we have nothing critical to do, just Linux gets some time for the calculations. Otherwise, the microkernel will just give the CPU to the critical tasks. So these have been the very first approaches of making real-time Linux. And actually, I've been using these approaches when I got into this topic. So at a first glance, actually, this approach looks pretty clever because, well, we just have that microkernel and we don't have to touch Linux, right? But if we think about that sometime, we will recognize that there's actually two problems with that approach. Basically, we need to port the microkernel to all the hardware, which is actually already supported by Linux. So you need people porting it over and over again to new hardware. And you can be sure you won't get such a big community for a microkernel as you already have for Linux. So this is actually a big deal. And well, the second issue is, you can see Linux is not running on the hardware actually. So we need, to keep Linux happy, we need a hardware abstraction layer, which also needs to be maintained for every new Linux version. So, you know, Linux is developed really, really fast, so this is a hard issue. So basically, statistically, like 8 to 10,000 lines of code are changing each day in the Linux kernel. So these guys really have a hard time to maintain this hardware abstraction layer. So at the first glance, it looks quite clever. At the end of the day, they are really having a hard time to maintain their stuff. So that's the reason why people always kept thinking, if it wouldn't be possible to find a way to modify Linux in a way that it can have deterministic timing behavior. So people actually are still working on that, and actually, well, I can tell you right now, they found a way to do that, and this is basically the real-time preemption patch I want to talk about later in my presentation. But let me give you, first of all, some quick examples about microkernels which are still around. One of the most famous examples is the RTAI kernel, which is called the Real-Time Application Interface. And that was actually the first real-time Linux derivative I was using in my life. It was developed in Italy. It's still maintained. The project is still there. It's a very classic microkernel approach. So if you're using RTAI, what you're basically doing is you don't write an application. You have to write a simple kernel module with a special API, no Linux API. It's basically, well, the API this microkernel is offering, and this, well, kernel module gets hooked up to this microkernel and does the real-time critical tasks. That's actually pretty hard to handle because usually application people also need to deal with the real-time stuff, and now these guys need to start to implement things in kernel space, which is way harder. It's a bit harder to maintain, hard to debug, and actually there's another issue for industrial customers because, well, if you need to put it inside the kernel, it's for sure it's GPL, there's no other option. This is not always possible for industrial customers to put their whole application under GPL, though they have to think how to split stuff. They have some limited support, like to hook up a Linux application with a microkernel that was called LXRT. I have to admit I haven't used it in a while now, but for me it never worked really out. So when I was using RTAI, basically I had to use the kernel option to get real-time requirements. So the design goal of RTAI always was to get the lowest latencies on a given hardware, which means that they only have a very limited number of supported hardware platforms. It's really hard to port. So basically, nowadays they have x86 support, 32, 64-bit, and they have ARM, and that's basically it, so not much more. So if you have a look at the design of RTAI, you can see, once again, it's the classical microkernel approach. So this part is handling real-time. So for real-time scheduling, you will basically stay in kernel space. And you can see here Linux is just running as a low priority task on top of that microkernel, and they need that hardware abstraction layer to keep Linux happy. And they have a simple communication mechanism to synchronize the real-time and the non-real-time world. So that's basically the concept of RTAI. The project is still there, it's still maintained, you can still use it, but actually it has a lot of limitations. So nowadays we don't see many people still using it in new projects. But there's actually another approach, which actually was started pretty much at the same time like RTAI was started. This is called Xenomai. It's also a dual-kernel approach, founded in 2001, so it's existing for more than 15 years now. Well, the design is basically pretty much the same in comparison to RTAI. But they actually took some clever decisions. What they also wanted to offer is a nice interface to hook up a Linux user space task with the microkernel, so you could actually have real-time in application and user space, which is basically what you want to have. It's way easier to handle for your application developers, and it also works around the licensing issues. And this actually worked out pretty well. So we've been using Xenomai like 10 years ago. That worked pretty well. And they also had another nice idea, which they called the skins, which is basically rebuilding or emulating the API of other real-time operating systems. So the idea is basically, if you have a pre-existing code base of your application for another operating system like PSOS, or they even have a POSIX skin, you can just link that application on the appropriate skin to have a rapid prototype and do some tests on Xenomai and see if your application meets the timing requirements on real-time Linux. So that was actually a pretty clever technology. It also was way more portable than RTAI, so they have way more supported platforms like also x86, 32, 64 bits. They've got PowerPC, they've got ARM, they've got a couple of more. So it was quite good maintained, way more usable because you have real-time in user space. But well, at the end of the day, they still have two problems, like the usual problems the microkernels have, like it needs to be ported to every single Linux version, and it needs to stay up to date with the new hardware, so they also have a huge effort for maintaining it. Yeah. Well, this is basically how Xenomai looks like. You will recognize it looks pretty similar to RTAI. So basically we've got this microkernel, we've got Linux running as a low priority task. But you can see this path which is going straight to user land. So you have a clear option to have real time right here in your Linux application, which makes it way easier to use. So it's way easier to use, but you have to be aware that on that point you need to use special libraries and special APIs. So this is not a standard Linux application. You have to link against the Xenomai libraries, like in that case you will basically just use the so-called POSIX skin. So it's not just linking against the standard C library, you still need special tools and special API for your real-time application, which makes it also a bit harder to use than a standard Linux application. So I tried to summarize some drawbacks of the microkernel solutions. So basically, as I mentioned right now, you have a special API, you have special libraries to use, which makes dealing with that quite hard. You've got the porting efforts, the maintenance efforts of the people who are doing the microkernels. That's actually a big problem. And well, there's actually a couple of people who still can't use it because it's a microkernel which is basically, they don't scale pretty well on real big platforms. Like it's not a big deal for embedded platforms. But just remember, we've got people in the financial service area using real-time Linux on real big machines. And well, the microkernels just won't scale good enough to be run on these machines. Because these microkernels would just spend most of the time for synchronization on these machines. So that just won't work out. So for that reason, there were two guys who always kept thinking, how can we make Linux itself capable of real time? And well, these two guys came up with a technology which is called preempt RT, or you might have heard about the so-called real-time preemption patch. So these guys actually found a way to make Linux itself real-time capable. So these two guys were Thomas Gleixner, which is actually the founder of Linutronics, and Ingo Molnar, who did a lot of scheduler work in the Linux area within the last 10 years. So these two guys actually started pretty much at the same time working on real-time Linux, and at some point they started to coordinate their efforts, putting it together, and actually they came up with that patch. You will see, I will tell about that. Already many things of these two guys hit mainline, so many things they're using nowadays in Linux were originally designed for this real-time movement. And the idea of these two guys was, instead of using special tools, well, if Linux itself is capable of real-time, you can just write a POSIX application using the standard C library. So it's way easier to maintain, and we can reuse all the drivers which are pre-existing in Linux, and we don't have to port it over and over again. So actually, the thing is, these guys had to touch the whole kernel. So that's why it took quite some time, like 10 years now. So now they're pretty close to get it mainline, but they managed it, and they have a huge community right now, and they have a huge acceptance in the mainline community, because what they did is, like, they did not just add real-time features, they also added a lot of stuff which is also useful for people who are not relying on real-time, like the tracing infrastructure, the high resolution time, and all that stuff. So it's always also adding useful features for other people, and that's actually the main strategy you should follow if you put things mainline. Not just think about use case, just think how could other people use that for their own use cases, even if they don't have the same requirements. So that was actually a pretty clever decision. So they got a huge acceptance in the community. So now, how did these guys manage to get Linux itself real-time capable? So we have to remember the main requirement we have for real-time Linux is we need preemption. So what they did was they came up with a couple of ideas to get more preemption into the Linux kernel. So what they basically did was, well, that was basically the most improved change. They came up with the idea of the so-called sleeping spin locks. That's the reason why you might have heard about real-time preemption also, as was called for some time the sleeping spin locks patch. It's basically changing the behavior of the locking primitives. They also came up with the idea of interrupt threads, threaded interrupt handlers. So their idea was, instead of running interrupt code in a hard interrupt context, they will just wake up a kernel thread, and you run the code in a kernel thread context, which is basically interruptible, and you could put a priority on it. So at the end of the day, what this patch set does is it just introduces a new preemption model. That's what you will see as a user. You just patch your kernel, you configure your kernel, you just select preempt RT full as a preemption model, and that's it. There's nothing special about that. So at the end of the day, to make the story short, the main aim of this patch is just to minimize the amount of kernel code which is non-preemptible. So this is basically the main idea. So it's easy, right? But it took quite some time. So let me go a bit more into the details about the sleeping spin locks. So what they basically did was, if you enable the full preemption, the real-time preemption for your kernel, the spin locks will automatically be converted in so-called sleeping spin locks, which can be interrupted. And if you need the original behavior, if you need to stay atomic, what you need to do is to use the so-called raw spin locks. So they changed the default behavior, everything was preemptible, and they had to identify the sections which had to stay atomic. That was basically the idea. If you disable this preemption model, behavior will just stay the same. What he will do is we will just map the spin locks to the so-called raw spin locks. So we'll just keep the original behavior if you don't have that preemption model enabled. That's the basic idea. So apart from that, I mentioned the threaded interrupt handlers. basically what preempt RT will do, every interrupt handler will be forced to run in a thread context. So we go to the interrupt, just wake up the kernel thread, and that's it. The rest of the code will just be run in the thread context. So this is the default for all interrupts except the timer interrupt. So this is the only one which will keep on running in hard interrupt context. You still can force for critical interrupts that they need to be run in interrupt context. There's just a flag you need to use. It's called IRQF no thread. Then it will just put it into the original behavior and run your handler in the interrupt context. And this is actually one feature which already hit the mainline kernel. So you can already use threaded interrupts on mainline. So you can take the decision during the time when you register the handler, or you can even force the preempt RT behavior just by booting your system with the thread IRQs option. Then it will just by default put every handler in a kernel thread context. So this will basically look like this. This is just a quick snapshot from my laptop. Every interrupt will just show up in the process list as a kernel thread. So it has a PID, and it will, all the interrupt handlers will come up by default with a SCED-FIFO strategy with a priority of 50. So that's the default, and well, you can change it during runtime according to your needs, so you can give a higher priority to the critical work you have to do on your system. So they actually had quite a few clever ideas to maximize the preemption in Linux. So now I told you one of the disadvantages of the microkernels is that they are quite hard to use for user space. So you need special libraries and stuff. So the main question is, how does user space deal with the real-time preemption patch? And basically, that's the nice answer. Basically, user space won't even recognize. Because it's a standard Linux system, we're just underneath changing the preemption model. But you're just writing a standard Linux application. And if it's a critical application, you just put it on SCED-FIFO or SCED round robin, which basically means, well, you just write a POSIX application. You could go to a bookstore, buy a used book, 30-year-old used book about POSIX programming, and that's telling you how to use preempt RT. That's nice, right? So basically, for user space, it's not a big deal. So this would basically be the picture if you look into preempt RT, and you will see that, well, it's just a standard Linux system. So now I have mentioned that we're on the way getting this technology into the mainline kernel, and it has a long history. So that history started in 2006. So that's a statement from Linus Torvalds. These guys have been talking about, well, if it would be an option to get real-time into the kernel, they've been talking about that during the kernel summit. So Linus was asking about, well, do we have any users for that? And well, Thomas actually, he had one user, he was producing welding lasers, so they have real hard timing requirements. So he was like, yeah, well, I have already one customer using that with welding lasers. And Linus was like, well, that's kind of crazy, right? But well, anyone who's doing Linux is a bit crazy in its own way, so well, feel free to get that mainline. So that was actually basically the starting point where people contributed their stuff for the mainline kernel. It's a history of 10 years now, and we're getting pretty close, so it's not much missing to get everything in the mainline kernel. So how does it look like for the user? If you want to use that real-time preemption patch set, basically it's a simple patch. You could download at kernel.org. Basically, it's available for every second kernel release, and we also follow all the stable releases Greg is doing. So you get releases for all the stable kernels and long-term kernels, basically, which are done. So that's the most important thing to know. If you follow the history of the project, you might see that the mainlining efforts at some point calmed down a bit. Well, actually, they have been stopped. So if you're wondering what was the reason for that, is basically there was some time where we actually didn't have a funding for this huge effort. And what basically happened is what's happening for most of the technologies, if they are getting good enough, people are just using it because it's working, but they just stop contributing to it. So we've been in a situation where just people heavily used that patch set even in industrial controllers, but no one was contributing to it anymore. So that was actually getting into a bad situation. So the maintainers decided to escalate things and tell people, well, we need help, we need some funding for the project, which was quite important. So then a German organization, the OSADL, jumped in. They care about Linux in the automation industry, and they guaranteed the funding for at least the maintenance of the real-time preemption patch. And sometime later, Linux Foundation, that was in 2015, started a big funding. It's called the RTL, Realtime Linux Collaborative Project. Basically, they guarantee that there's a funding for maintaining this patch set and getting it mainline. So actually, people are getting paid to get these technology in the mainline kernel, funded by Linux Foundation. That's actually pretty cool. So we have a working technology and we have a big organization behind it. So who's basically doing that work? As mentioned, we have this Linux Foundation project, which is funding the work. Well, we've got Thomas at Linotronics doing most of the mainline development and all the new development. You can actually follow the testing on this address. We've got way more people on it, like I told you, we're following the stable kernels. So we've got Stephen Rosted maintaining most of the stable trees, and we have got Julia Cartwright maintaining 4.13 these days. Actually maintaining the old trees is quite important for the industrial customers, because the problem is they usually want to stick with the kernels they have. They usually don't want to keep up with the newer development. It's usually hard to convince these people. So it's quite important to have maintenance for the existing kernels. Well, just to give you a few examples, which features are already mainline. Well, we could spend a whole presentation on that because we have so many features already mainlined. But these maybe are some technologies you might know. So, well, even if you know or not, you're definitely using high-resolution timers on your systems. So basically, in the good old days of Linux, just the timers had a granularity of the scheduler tick, nothing more. So for real time, we needed high-resolution timers which had microsecond resolution. This is what Linux does today, or Linux can do today, and this development just came in from the real-time people. The same for the threaded interrupt handlers, which are mainline, and most probably you might have used the tracing infrastructure so far. So most of that development was also designed by the real-time people. So there's many features which are just useful for everyone, which have been designed by the real-time guys. Here's just a quick example of work we have recently accomplished. Well, we did a rework of the CPU hot plug and CPU hot plug locking, which is like, that's kind of some part of the kernel where, well, people kept fixing it during the last few years just by putting more duct tape around it, right? So actually that bunch of duct tape hit us straight in the face for real-time preemption, so we had to fix that. They did a complete rework, which was posted and actually merged. So this is something we accomplished recently. If you're really interested in that and want to follow the mainline development on that, there was a recent talk like 1.5 weeks ago in Prague by Sebastian from the real-time team. He did a very good status talk about preempt RT, what we mainline, and what are still the tasks we need to accomplish. So the slides are online, it's on YouTube. So if you're interested in following that development, I would highly recommend to check out that talk. If you're looking into more technical documentation and even if you want to participate, which would be much appreciated, right? You could check out that wiki on linuxfoundation.org. Well, so last but not least, I promised that I will show some latency measurements just to tell you which latencies are possible with real-time Linux. So, and these are just measurements. People usually ask us, do you guys have any mathematical proof on your real-time system? Well, no, we don't. It's not because we are too lazy or we don't want to do that. Basically, at the end of the day, I would say it's just impossible. Well, the code base is huge, but we might be able to manage that. But the thing is, we don't know how today's crappy hardware will run the code. We just don't know what happens inside the hardware. So we have at least 2 levels of caches. We've got instruction pipelines which could actually reorder the instructions. So we actually don't know how our code is executed, so we can just evaluate it. And that's what we basically did. We picked up a Cyclone 5 based board. It's Cortex A9 ARM dual core. We fired interrupts with 10 kilohertz. We've been using a nice box. It's the so-called OS-ADL latency box. So you can configure it to fire interrupts in a given time frame. And well, it has an input pin you need to trigger. So it fires an interrupt and then it measures the latency to the point where you trigger the input. So you can actually measure the reaction time and it will just record every sample and give you a nice histogram. And most importantly, the numbers we are interested in is not the average reaction time of the system. So the numbers we are interested in is the worst case we could guarantee. So we want to put the system in a worst case situation. And well, we've been using Hackbench to do so. Hackbench is a pretty nice scheduler benchmark. So you can give your system a real hard time with that. It's basically doing groups of clients and servers, 20 clients, 20 servers. Each client is sending each server 100 messages via a socket. So if you put 40 groups, it's 40 by 40, so it's 1,600 processes doing weird inter-process communication. So you will get 100% CPU load and a real hard time for the scheduler because he continuously needs to take decisions. This is basically what we're using for these evaluations. And well, we took the bare minimum for this measurement, which just took 12 hours, which is the minimum you should take, but well, the longer you take, the more accurate are the results you will probably get. So what we basically did was we wanted to compare the microkernel technologies with the preempt RT, because the reason for that was there's still many papers out in the web which are claiming that the microkernels are way better when it comes to latencies. And what we wanted to do, we wanted to do a fair comparison because preempt RT is way easier to use, so we wanted to compare it with microkernels and see which technology could give you the better latencies at the end of the day. And well, that was basically what we were measuring. Well, you have an external event coming in, like that's me this morning. So alarm clock was ringing. It took some time because I had some beers last night. So there was some reaction time to the alarm clock. So that basically we measured the same for the real-time system. And we actually measured the most important use case. So we wanted to know how long does it take from the interrupt arrival up to the point where a user space task could probably react to that event. That was basically what we did at that point. So we started with the Xenomai, the classical dual-kernel approach. You can see the average is like at 30 microseconds reaction time, but you know, we want to see what's the worst case guarantee. So we have one peak right here, see that? At around about 95 microseconds. So this was within 12 hours the worst case timing requirement we could possibly guarantee with a Xenomai, which is actually not too bad on that board. So we did the same measurement on preempt RT. Well, you see the average, it's a bit worse, so you have a bigger jitter. But if you compare the worst case, it's pretty much the same as for the microkernel. So that actually proves that we can actually be as good as the microkernels with the reaction times when it comes to the worst case. So we've been like 95 microseconds for both use cases. And now the cool stuff is coming in. Since it's standard Linux, you can use all the standard Linux features for doing optimizations. So what we did, there was a dual core system. We've been just curious if it could have an influence if we just isolate one CPU for handling this specific interrupt. And that actually shows you that we've been able to get the latency down to around about 80 microseconds. Just a simple feature, standard Linux feature. So that was quite cool. So if you compare the results, you can see the green line, the green peak is Xenomai. The red one is preempt RT. So the latencies you could achieve are actually nowadays pretty much the same. Well, preempt RT is way easier to use. Well, finally, we did another measurement. Not because it makes sense, it doesn't make any sense at all. But there's a lot of these benchmarks around in the web comparing the latency on the kernel side, comparing the microkernels and preempt RT, and that's basically comparing apples and pears. Because you're comparing a general purpose operating system with a small microkernel. So, well, doesn't make any sense at all, but these measurements are around and they usually also want to prove that the microkernels are way faster. So we've been just curious what we could do on preempt RT side. So this shows the kernel latency for Xenomai, which is quite good, 30 microseconds, worst case latency. So if we compare that with preempt RT, we are still at around about 90 microseconds. It's pretty much comparable to userland because what we do is basically waking up a kernel thread. So the latency is pretty much the same, but what we did right here, we also tried to isolate one CPU for this interrupt. And basically, we've been able to get it down to around about 60 microseconds. So this is a bit slower than the microkernel, but you know, it's standard Linux and it's a full-featured operating system. So I think this latency is still quite good. And we actually did one last measurement because, well, you know, if people are willing to use a microkernel to get better latencies, they are willing to accept some restrictions, right? So I was wondering, if we accept some restrictions on preempt RT, is there any option to get the latencies a bit more down? So what came to my mind is, we've been running on ARM. I've been just curious, what would happen if we could use the so-called FIQ context? It's a fast interrupt. It's a special thing on ARM CPUs. This is not code which is running inside Linux, just like some interrupt vector to run to. It's pretty special to ARM. But I was just curious what timings we could guarantee on that CPU, and that pretty much shows that the worst case latencies are really limited by the CPUs right here. So if you're using that on preempt RT, you also get down to these 30 microseconds, and that was pretty much the limit we've been able to hit on that SoC. That was, yeah, the best latency we could possibly get. So as you can see on the kernel side, for sure, the microkernels are way better. But once again, it's comparing apples and pears. But it also shows that the in-kernel approach is actually not behaving too bad on the kernel timing. So if we take a conclusion at the end of the day, we can say, well, the microkernels are quite hard to handle. They are still there. They are still valid use cases, but they are pretty much hard to handle because they need to maintain the microkernel. You need to use special libraries and tools and stuff. And we've been able to prove that the microkernels do not have better latencies for the most common use cases. Like for the user space latency, it was pretty much the same. So at the end of the day, we have preempt RT coming up as the de facto standard, showing pretty good results. It's the technology which went mainline. So as you might expect, this is the recommendation I would give to you guys if you have real-time requirements. This is the technology you should check out, and check out the real-time preemption patch. So that was pretty much all I wanted to tell you about real-time Linux. I think we still have time for some questions. Just for your information, I'll be around for the rest of the conference, actually until Monday morning. So if you have any detailed questions, feel free to ask. Thanks for your attention. Thanks for the invitation. And well, if you have any questions right now, feel free to ask.
Thank you very much for your presentation. It was very interesting, especially the real data. So now we have about 15 minutes for questions. Okay. Yeah, the first one.
Hi, thank you for the presentation. I have a question about this Realtime Linux Collaborative Project from Linux Foundation. As you said, it was started in 2015, and at that time it was said that preempt RT patch will be integrated during next 2 years. What our next date?
I was expecting that question. We usually get the question about the timeline, right? So one usual answer is next year, which is always true because we always have a next year, right? But to be honest, well, there's still timelines behind that. My expectation is like, well, once again, I could say another 2 years. But the thing is, if you're mainlining stuff, it's really hard to tell how long it will take, which discussions you have to follow. So we've learned from a couple of things, like we tried to do some prediction for the CPU hot plug rework, and it took actually way longer than we have expected. So it's really hard to give a timeline when mainlining stuff. Well, everyone who's doing mainline work knows how long it could possibly take. So basically, the standard answer would be, well, we would come up with a timeline when things are mainline, and that timeline would be very precise. Yeah. But I would expect like one or 2 years, but it could be more. We just don't know how many discussions we have to follow. But I have a good feeling that we're pretty close.
But RTAI collaboration project doesn't have any limits on date or deadlines?
Well, they have a yearly meeting where they just discuss about the next milestones. So basically what the project does, they meet on a quarterly basis, just discuss on what we already got mainline and what would be the next step. Yeah.
Okay, thanks.
Thank you. There's the next question.
Thanks for a nice talk. 2 questions. First, maybe 4 years ago I read that Linus told that priority inheritance is bad initially by design. But then you mentioned that it is mainlined. How does it happen?
Well, actually I can't tell all the details about the mainlining discussions. I know it was a hard discussion, and I think Linus said something like, friends do not let friends use priority inheritance or something like that. Well, it was a long discussions, but I wasn't involved in that development, so I actually can't give more details on that. But if you want to, you can check out Sebastian's talk, or I can get you guys in touch, so he should know all the details about that.
And, I really glad to hear that this big patch is coming to mainline. You may heard about jar security patch for the security features. It is really big too, but not such successful, speaking about mainlining. And what is the reason of such success? How would you describe it?
Well, I think the main reason for the success was that they managed to improve the quality of Linux for all other users. So the good thing they did was they always thought, how could we improve Linux for other users, even if they don't have real-time requirements, like the tracing infrastructure, the high-resolution timers and all that stuff. So I think that was one main reason for the success, and just from its nature, that's the next reason why it was so successful, since now the complete kernel got interruptible. A lot of race conditions and locking issues have been found, which have been always there in the kernel, but they just didn't pop up because we haven't been preemptible. So these guys fixed all these race conditions and improved Linux itself, fixed a lot of bugs, and that got us a lot of acceptance in the community. So I think that was the main reason why it was that successful. It just helped to improve Linux for everyone and not just for real-time users.
Thank you.
Questions?
Thank you.
Thank you for your talk. It was really nice to get that kind of high-level overview. Actually, 2 questions. The first is, okay, it looks like real-time Linux is very nice in different areas, so there are a lot of benefits of using that. So what are downsides of that thing, or let's put it like that? So if it is that good, from different points of view, why not we switch to it like for everything? And the second question, probably a little bit naive. You showed us a couple of pictures with latencies that you may reach, but what if you need to get even shorter latency? If there is a way to achieve it, or you have like 100 nanoseconds or microseconds and you can be even more responsive?
Okay, let's start why shouldn't everyone use it? So basically you need to think about your use case. If you don't have hard real-time requirements, you actually don't want to use it, because the thing is, you need to think, what do I want to optimize for, right? So for the standard user, he usually wants data throughput, right? But if you want to have deterministic timing behavior, that will just reduce your throughput because you can't.
Yeah, so that was the question. What's our downside? So what are we trading?
Yeah, so the downside would definitely be if you enable the full preemption, basically you will reduce the data throughput. So that's basically for sure because that's because of the nature of real time. So this would be definitely the drawback when enabling that option. So that's the reason why you should only enable this if you really have the real time requirements. And for the next question, well, it has limitations. Yeah. So with the real-time Linux, we need to be aware it's a full-featured operating system, so we definitely have some limits for the latency. So if you have to go down to nanosecond or just lower microsecond resolution, this is nothing which basically would be possible on this platform using Linux. So this is basically why still other operating systems are around, which could achieve that, or other people just do these use cases in an FPGA. You've got modern CPUs.
So
yeah.
So in the end, you get what you get. You cannot.
Yeah. At the end of the day, you get what you get. That's the problem. I told you that it's really hard to do a mathematical proof or a prediction which latencies you could achieve. So if you're thinking about real-time Linux on your platform, the only thing you could possibly do is just to run it and evaluate it and see what's the worst case you could probably hit. Yeah.
It makes perfect sense.
Okay. The next question.
Thank you for talk. I just trying to understand, do you have some successful deployment for RT patch in industry, and which industry is it?
Well, yeah, there's many. There's actually many I'm not allowed to talk about, but well, the most, so I gave one example, like we've got big machines running welding lasers with preempt RT. Another example is woodworking machines, which is like doing furniture for IKEA and stuff. Like, so those machines also running real-time Linux. A lot of machine controllers, numeric controls and stuff are running real-time Linux, multimedia systems. Yeah.
Okay, so thank you. One more question.
So you mentioned the FIQs. Why don't we use FIQs if they are faster?
Well, because they have a couple of limitations. So yeah, that's the reason. So I didn't explain the FIQ context properly. So you're right with that question. It's a very specific context you're running in, and basically you're not using Linux API on that point. It's just basically you implement a very simple interrupt handler, and you're very it's like you're like in a jail in that context. So you basically, the CPU allows you to access most of the peripherals, but yeah, you're just caught in that context, and it's actually not real Linux context. So that's the reason why we won't use it generally, and on the other hand, not all CPUs do support it, right? So it's ARM specific, and not all ARM SoCs actually do implement the fast interrupt context.
Thank you. Any more questions? Okay, Sim.
I have another question. Could you show a slide with the diagram?
Yeah. Which one?
I think it was the first one. Oh yeah, this one.
That one?
Yeah. Here you have RT USR modified. What does it mean?
Well, that was, I just skipped that one. We tried to use, during that time frame, we tried to do some optimizations for the high resolution timers and stuff. Mm-hmm. Well, the thing was we tried to check out, so we got some bad latencies when our interrupt arrived pretty much at the same time when we had to handle a timer interrupt. So we tried to figure out what we could do on that, and actually I included that measurement right here. So that was just some testing we have done during that time when we did these measurements.
Yeah, okay.
Okay, any more questions? Actually, a question to you, Jan. What is the best question you received?
Well, that's actually hard to decide, but I would say the best question is, well, the question about the timeline. This is probably the best question.
Okay.